Namaskar everyone. Welcome to the last topic of this cryptography series, and this topic will cover noisy and noiseless channels and quantum cryptography. So let's start with the video. So let's recall what we have studied till now. In cryptography, we have a sender A and a receiver B with eavesdropper E. A and B are connected through channel C, and eavesdropper is also trying to get the message which is being sent. For eavesdropper to not get the actual message, the sender encrypts the message and converts into the ciphertext using a key which is being shared with the receiver via secure channel. Then the ciphertext is sent through the main channel and the receiver decrypts it with the help of the key itself and gets the correct message. As eavesdropper don't have any key, it cannot understand the message. Now, some assumptions we have already considered into our account, that channel gives no error in ciphertext sent. Also, secure channel ensures error-proof key sharing. Isn't this really ideal? What's real is channel may introduce some errors or noise. Why? We'll talk about it later. But consider is a perfect channel which will never introduce kind of error, which is very less possible. So, also, how to deal with this noisy channel so that we can ensure correct delivery. So, these are some problems we are going to face when we use noisy channels, and we will see how to deal with them. So, noiseless channels are like dreams. They are perfect and they are non-existent. In noiseless channels, the transmission faces no error, and it's a very simple code for the noiseless channels is day or night, delivery all right. But that is not very possible. Noisy channels. Noisy channels are the reality and they exist because mistakes happen. How? As there might be several cases in which channels hinder the message that is being sent. Physical problems like storm and rains, earthquakes, the channel might break, or just bad quality channel. Otherwise some other noises, but let's suppose these are very pretty easy to understand cases. Now we need to rectify these errors via some methods. So we can consider it as error correction. Now, basics of communication theory. To understand how to improve the performances, we just need to recall our basics of communication theory. First, bits. They are the smallest unit of data. They can be considered as 0 or 1, yes or no. And as Amitabh Bachchan quoted, no isn't a word, it's a complete sentence. Bit rate. Number of bits transmitted through channel per second. We can understand that we know that sometimes Wi-Fi speed shows us 2 Mbps. That means 2 to the raised to 2 into 10 to the power 6 bits per second. Throughput. Number of frames, instructions or units transmitted in unit time. Bit rate is kind of a throughput. Hamming distance. This is racism between frames. Discrimination. Just a joke. How different are two frames? We need a measure to a method to measure that how different are two frames bitwise. So let us suppose we have sent a frame 1100101110 and received the frame 111011001. So let us see which bits have changed. The first bit is 11, so not changed. Then 11 not changed. 01, yes, it has changed. 00 not changed. 11 not changed. 01, yes, it has changed. 10 changed. 10 changed. 01 changed. So number of bits that have been changed is 5. So this is the Hamming distance between these two frames. Now entropy. Entropy term, when we hear, it comes that we consider the thermodynamics we used to study in higher secondary, but this is not that entropy. Okay, here entropy is related to random variable. It defines average level of randomness inherent in possible outcomes. Suppose we have a random variable, so the average level of randomness that is possible in the outcomes that we are gonna get. Suppose we have a dice which is unbiased, then the probability of get every outcome out of the 6 possible outcomes is 1 by 6. So entropy is defined as summation of minus probability of an outcome into log of probability of that outcome whole summation. So we can calculate that for a dice the entropy is minus log 1 by 6. Mutual information. What entropy is for one random variable, the relationship between two random variables is defined by mutual information, that is represented as I x semicolon y. What mutual information measures is mutual dependence between these two random variables. So mutual information between x and y is defined as entropy of x minus conditional entropy of x given y, also equal to entropy of y minus entropy of y given x. Channel capacity. The maximum rate at which information can reliably transmitted over a communication channel. This is the maximum possible transmission rate which we can say that reliably transfers the frame from sender to receiver. It is calculated as the maximum for all the x's for all the outcomes, maximum of all the probabilities for all outcomes, the mutual information. We will see how we will calculate that. So to study noisy channels, we have to consider two models of noisy channels, which can be the cases how the error is being introduced. Although actual noisy channels can be a mixture of these two cases or some new cases which is beyond the scope of this lecture, but we will just try to study these two. So in a binary symmetric channel, the first case, we have the probability of error p. That means in binary symmetric channel we have the input as 0 or 1 and output as 0 or 1. If an error comes, then 0 is converted to 1 and 1 is converted to 0, but none of the bits are dropped. So the probability with which error can occur is p. So with the table we can see that if we have input 0 and we get an output 0, the probability is 1 by minus p. The probability that we have input 0 and we get 1 is p. The same is for 1 0 and 1 1. There is another type of channel, that is binary erosion channel. Here the input can never be converted to the other case, like 0 will never be converted to 1 or 1 will never be converted to 0, but if the error comes, the bit is dropped. So when the bit is dropped, we consider that case as star. You can see that we have input 0, so the probability to get 0 is 1 minus p and probability to get 1 is 0, but probability to get star is p. Here p is the probability of dropping. The same is for the 1 case. Now we will see in the later slides that we will require maximum likelihood estimation. So I would like to introduce to maximum likelihood estimation to you. Suppose we are given a random variable and we get some probabilities. Now we want to find a distribution, the data which suits the best to this outputs. Now we have an output and we guess the distribution, but actually what we does is probability distribution we have, we submit an x variable and then we get the probability of that outcome. But here we go in reverse. We have a probability and then we guess the distribution function it belongs to. How do we calculate that? PDF is defined by mean and sigma square, which we put into a formula. Suppose we have used a Gaussian, we have that formula 1 by 2 root of 2 pi sigma e raised to minus x minus mu square upon 2 sigma square. So we actually optimize the value of mu and sigma square so that we get the exact probabilities which we have as our outcome. I'll try to attach some resources so that you can understand the maximum likelihood estimation better, or you can just wiki it. Now, to calculate the channel capacity of our binary symmetric channels or binary erasure channels, we first need to encode the symbols. Suppose we have a message m of length L. Now we have to convert into the block of input symbols of length n. So assumption is the length of message is L and input set we have is 0, 1. This is just a general consideration. Now length of encoded message em is n and output is also defined in 0 or 1. So we can define a function e such that 0, 1 set of 0, 1 raised to L is converted to 0, 1 raised to n. Now the range of e is also known as code words. This range is called mn. I forgot to mention the point that for binary symmetric channel, if we have a length as n, then the probability of error is 1 by p raised to n. You can see. Now decoding of channel codes. As we need to, we are encoding it. Now at the receiver end, since there is a probability that this frame is not the actual frame, what we get the frame, we have to predict which frame it actually belongs to. For that, we need the probability distribution function of the code words and also the channel. Suppose we get a code word m which belongs to the range mn received by the receiver. Now decoding function gets this message and predicts the message. So if we, even if the message is null, if we don't get a message, we get null as a message, we discard that frame. So now how do we calculate that decoded message? We get the maximum probable message that belongs to this code word in the distribution. We ask the most likely code word m belonging to mn sent in one distribution defined by sigma. Sigma here is various. Knowledge required for decoding is probability distribution function of the code words and the channel. Here we can see that ideal observer must be the maximum likelihood function which guesses the actual message with the help of received message. Now we try to calculate channel capacities for binary symmetric channel and binary erasure channel. Suppose we just studied in channel capacity that it is the maximum of the mutual information between two random variables. Here the first random variable is the input and the second random variable is the output. So mutual entropy between them is the entropy of input and the conditional entropy of given received message, the probability of input. So now we get this formula C is equals to max of S belongs to S, which is input, I S given T. Now in binary symmetric channel, source we have 0 or 1. Suppose the bias we introduced is alpha. So the probability of error is alpha. This is symmetric around alpha equals to 1 by 2. So the probability of 0 to 1 is 1 by 2 and also 1 to 0 is 1 by 2. We can calculate that the maximum convex is at also belongs to alpha equals to 1 by 2. So to calculate H S given T, we can just put the probabilities as it is. The probability of 0 given 0, probability of log of probability of 0 given 0 for 0 1, for 1 0 and 1 1. We put the probabilities and we get the answer as minus log 1 minus p into 1 minus p plus log p into p. As we know that the entropy of input is 1, therefore we get the channel capacity of binary symmetric channel as 1 plus 1 minus p log 1 minus p plus p log p. You can try it yourself. Now for binary erasure channel, we assume that unbiased bit source. Unbiased means all the cases are equally probable, so equal probability they have, maximizes the channel capacity as we used a binary symmetric channel. As the probability of 0 to 1 and 1 to 0 0, these two cases will not be included in our analysis. Then we put the probabilities 1 minus p by 2 log 1 plus p by 2 log p by 2 plus p by 2 plus log p by 2 plus 1 minus p by 2 log 1. we get the answer as P. This is h of s given t, and we know that h of s is 1. So the binary for the channel capacity for binary erasure channel is 1 minus P. I hope I would have been able to clear some understanding. In future lectures, we will see Shannon noisy coding theorem and some protocols for noisy channels. Also, we will study quantum cryptography. So, I would like to end my lecture here.